We need to cut the sci-fi metaphors. Machine learning isn't magic. It's a fundamental shift in how we write software. For decades, we wrote explicit, line-by-line instructions, imperative programming. You own the logic, and if there's a bug, it's your fault. ML flips this. Instead of writing the logic, you write the scaffolding for the logic to emerge. You define the model and the loss function, and then feed it a massive firehose of data. The optimization algorithm then tunes the internal parameters until the model derives its own rules. The data writes the logic. We've traded direct control for complexity. Machine learning is typically carved into three major domains. The distinction is critical, as it is dictated entirely by the structure of the data you possess and the specific problem you are trying to solve. Supervised learning is the industry workhorse. We have labeled pointers, a giant key-value store where every input has a known, correct output label. The problem is function approximation. We need to find f, x, equals y, but the rules are too numerous or too subtle to write ourselves. The model tunes its weights to correctly map new, unseen inputs to their corresponding outputs. The key constraint is the data bottleneck. Supervised learning lives and dies on quality, labeled data, which is often a massive, expensive, human-powered operational cost. The classic failure mode is overfitting. The model memorizes the training data instead of learning a generalizable function. It's like a cache that only works for the exact memory addresses it has seen before. In unsupervised learning, you have no labels, a raw disk dump without a file system. The goal is to find latent structure within this undifferentiated mass. Common tasks include clustering, where the algorithm partitions the data into similar groups, and dimensionality reduction, which compresses the data by finding its most informative axes. Without labels, the discovered structure is subjective. You need a human in the loop with domain expertise to validate if the found clusters are actually meaningful. Furthermore, many of these algorithms are computationally brutal. Some scale quadratically with the number of data points, making it the system's equivalent of running a massive full table scan with a cross-join. Reinforcement learning is about sequential decision-making under uncertainty. It's not about static data, but an agent learning an optimal policy by interacting with an environment. The agent takes an action, the environment changes state, and provides a reward. The agent's challenge is to maximize its cumulative reward over time. The core challenge is credit assignment. Which action, among 1,000, earned the final victory? This leads to catastrophic sample inefficiency, requiring millions or billions of interactions, which is why serious RL usually happens in fast simulators. Training can also be notoriously unstable. Debugging an RL agent is like trying to find a Heisenberg in a massive, distributed, asynchronous system. ML models are brittle pattern matching engines. Failure point 1. Garbage in, garbage out. A model is a reflection of its training data. If your data is biased or incomplete, the resulting binary will be fundamentally broken. Failure point 2 is concept drift. When the world changes, say, new fraud vectors emerge, the model, static binary that it is, silently degrades, necessitating massive MLOps infrastructure. Finally, we face the opaque black box problem. With complex deep neural networks, the logic is encoded in millions of parameters. You can see what it predicted, but you can't easily ask why. It's a production system with no stack traces or debugger beyond its final output. This lack of interpretability makes ML a non-starter for domains where accountability is a legal or ethical requirement. ML is software, but it demands a unique systems mindset to deploy and debug.